Good to go now. Okay. I will wait a couple for people to get here. I'm not sure if everyone's here or not. Had some technical difficulties there to start. But the classic stop and restart worked, as it always does. Cool. I was about to ask you to do that, Tyler. Alright, I will mute myself now. Alright, so we are embarking on a new adventure into symmetric groups today. First, I just wanted to give a couple announcements. So one, I'm just scrapping the definition quizzes completely. I said originally we could do like oral retakes. I think it's just going to be too much time, and it's such a small thing that I just don't think having that extra thing while you guys have a project and problem sets and stuff is useful. So that's going to be retroactive as well. So if you had retakes or whatever that you needed to take, it doesn't matter. This is going to be worth 0% of the grade now. So basically just no definition quizzes toward as part of the grade. So that part will go toward probably the project and participation in general. 2, I will put YouTube videos of like math talks. YouTube videos of math talks up today for colloquium summaries if you did not go early and get those done, because we are not doing those even via Zoom or anything. And then, I mean, I guess just a general announcement, you have a problem set due Friday. It's a little bit different in flavor. It's more walking through kind of the stuff we talked about last week, right, with these cyclic groups, talking about those slightly more challenging proofs that use more like number theory kind of stuff that you probably aren't as familiar with, and so kind of trying to step you through step by step on that stuff. Okay. Any questions on things before we get started? Will I still put up definitions for the chapters? Probably not. I guess I could, but I mean they are all in the book anyway. But I suppose if you want me to, I can. I can pretty much just copy paste and edit a few things from when I did that last year. Any other questions on stuff or things as we get started here? Could be, actual content related as well, not just logistical. All right. Well, if I see something, I will answer it. So this last problem from our little like cyclic group section is an important one, especially towards the problem set, but also these groups of orders with like products of distinct primes and stuff. These show up a lot with CELO subgroups and the CELO theorems, which is something you would see occasionally in a second algebra class, especially a more group theory focused one. Some people will see it in a first algebra class. I know my office mate saw that in his Algebra 1. But those are some really cool theorems about kind of the structure inside finite groups. But this one is, what is this, 458? So I was looking through a few of these before class and seeing some common mistakes here. So I think this is definitely worth talking about. So let these be distinct primes. So this is important that they are distinct. Find the number of generators of ZPQ. So the cyclic group of order P times Q, where P and Q are distinct primes. Okay, so I saw a lot of good starts. So where do you want to start here? How do you know if you have a generator of a cyclic group? So obviously this is cyclic in the first place, right? Like this guy is definitely generated by 1, for sure. But how do we know what else will generate it? Any ideas? Yep, exactly. So, well, yeah, where in is something. Yeah, I'll slightly amend that. So it would be generated by, let's say, K, where the GCD of K and the order of our group, which is PQ, is 1. And so this is where it's important, right, that we don't have a prime here, we have a product of primes. Is PQ prime itself? No, right? It's divisible by P and it's divisible by Q. So PQ is most definitely not prime. So not everything inside there is going to generate, right? So what are you looking for? So for me, it's actually easier to look for the things that do not generate as opposed to the things that do generate the group. So maybe a better question is, what will not generate ZPQ? So, I mean, just from what we have above, it's if the GCD is not 1, right? If it's greater than 1. Can you figure out when that's going to be the case? Multiples of P and multiples of Q. Yeah, exactly. Exactly. So, I mean, P and Q are a couple of those, but it's more than just that, right? So, if you think about it, you start off with like P here, and then you have 2P, 3P, and so on until you get to Q minus 1P, and then finally QP or PQ, which is equal to 0 in ZPQ. Right, and so all of these guys, including 0, are going to be multiples of P, so they all share P with PQ. None of them will generate ZPQ. And similarly, right, we have Q, 2Q, all the way down to P minus 1 times Q. And then we also have, PQ. And so how many of these are there total? So how many non-generators, we'll call them? How many can you count there? Close. You're very close, Eddie. It's P plus Q. Do you see a repeat, though? This guy was counted twice, right? Yeah. So it's P plus Q minus 1. And so how many generators? Well, it's everything else, right? It's the rest. And so it's PQ minus P minus Q plus 1. And if you're into simplifying things or making this look interesting, this is exactly P minus 1 times Q minus 1. Right. Factoring. Algebra. We just did algebra. All right. Yeah, so this strategy will also work for your problem set problem, which is the next one where you have ZP to the n. Right, so there it's not distinct primes, but rather powers of the same prime. Right, so the first one works for things like Z6 or Z10, like 2 times 3, 2 times 5. This one would work for like Z8, where you have like a Z to the 2 cubed. And so both of these are important cases, but they have similar strategies for proving those. Any questions on that before we completely switch gears and start talking about the symmetric group. Or cyclic groups in general. Now is the time. All right. Fair enough. So we've seen the symmetric group before, right? We've talked about how it's generated by swaps. We've talked a little bit about how to write inverses in terms of swaps and stuff like that. But we haven't talked about it in exactly this context. So, right, we didn't really talk much about one-to-one and onto functions until we talked about isomorphisms. But now we have a better definition for permutation, right? Before we said it's like some reordering. But that's kind of a vague, hand-wavy definition. You can tell by the way I literally wave my hands. So a permutation on a set X, or I guess I'll use A since the book says A, the set A is a function, and we do usually use these Greek letters in this part of the alphabet, so like sigma, tau, delta, those kind of, well, I guess delta is in a different part, but sigma, tau, nu, in general Greek letters for permutations. So it is a bijective function from A to A. Okay, and by bijective all I mean is one-to-one and onto. Right, because you think about it, one-to-one means each thing goes to a unique thing, and it hits everything. And so basically everything is paired up with exactly one thing, and that's how you reorder, right? So that's the idea behind this, and it's a little more formal definition. And it also helps us realize it, right? So before we were talking about swaps, and we're like, well, you can view it as a function because it's like acting on this set. Mark, mute yourself. Then, all right, that just completely shook me. All right. So yeah, we talked about swaps, but like it was less clear how to define those as functions. You can kind of see what it's doing, and you could like create a function from it if you wanted. But this is just saying directly like every permutation is a function. Why is this nice? This is nice because we know function composition is associative. Right? We learned that very early. And so this automatically means that we get associativity for our group structure because our binary operation is going to be function composition. Okay. So that's one reason this is useful. Also, like composing things and all that is often just easier when you're talking about functions. You have to do less hand waving and picture drawing. But we're going to start with picture drawing. So while we will eventually not really draw a ton of pictures to describe permutations, we'll really adopt cycle notation primarily. It's useful, I think, to picture things via pictures. So we have these guys. So alpha, right, is going here, 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 right? So basically what you want to think of is you're starting at your top and then you're just seeing where it goes, right? So this is just saying like 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and then 5 goes to 1. So obviously in terms of like following in the book, this is getting a little ahead, but our end goal is to start talking about these things in cycle notation. So what is this in cycle notation? Someone throw that up in the chat. Yeah, exactly. It's just 1, 2, 3, 4, 5. And sometimes you'll see commas between these things. Personally, I guess I tend not to write them just because I don't like them. This is how I first saw it, and I am forever biased because of that. But just a fair warning. You may see notation that has that if you look elsewhere. But yeah, so this would be the cycle notation for this. And so your problem was to look at sigma, which was defined as follows. Boom, 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 boom. Okay, and then gamma, which is a more interesting picture. Cool, nice little symmetry there. So these two guys. Hey, how's it going, Bork? All right, so in words, which for me, like, that just meant basically saying what I said while writing this, right? If you're thinking about these in terms of how you would describe them to someone, I think the easiest way is just to tell them what is sent to what, right? If you're describing these in words. So for me, I'm thinking like, okay, 1 goes to 3, 2 goes to 5, 3 goes to 1, 4 goes to 2, and then 5 goes to 4. And notice I'm usually going like in this order. And so in terms of like finding cycle notation, like I usually always start at 1, see where that goes, and then, you know, wherever that goes, that's where I go next. It's just easiest to start left to right because this cycle notation up here, right, this is not unique. I can do any like cyclic permutation of this, right? Like I can basically rotate these around. So like this would be the same as 2, 3, 4, 5, 1, or, you know, 3, 4, 5, 1, 2. All of these are the same, but so as to not confuse yourself and others, we just kind of always start with, you know, 1, just because, you know, if I see 2, 3, 4, 5, 1, I don't want to think of this as something being distinct from 1, 2, 3, 4, 5. And so if I just kind of write it the most natural way, starting from the smallest, then I'll never double count things and stuff like that. And you can kind of see the same thing here, where I guess this isn't really preparing for cycle notation, but I'm just kind of going down in the way that makes sense. If I was doing cycle notation, right, I would go from here to here because I want to see where 3 goes next, right? And so what is this one in cycle notation? Can we figure that one out? 1, 3, 2, 5, 4. Yep, so, right, 1 goes to 3. 3 goes back to 1. Okay, so we close that guy off. And then, you know, you kind of start at the next highest thing. 2. 2 goes to 5. 5. 5 goes to 4. 4. And then 4 goes back to 2. And I close that guy off. Does the order matter here? Right, can I also, I'll put a question mark for a second. Can I do this? Does it matter? Say it with your chest, Clark. No question mark needed. You're correct. Yeah, no. The order does not matter. So why? So this gets at obviously a problem here, a few away. But why does order not matter here? What's the key? So yes, these are equal. Yeah, they are disjoint. And so this is where I think it actually is helpful to look at the picture, right? Because you can see that like the 1, 3 only affects vertices 1 and 3, while the other one affects vertices 2, 4, and 5. And so like they don't touch each other. They don't interact with each other. It doesn't matter in which order you do them, right? It's very similar to like the light switch group, where you're just like, well, the left one and the right one are completely independent of one another. And so it doesn't really matter in which order I do things. Okay, so how about gamma? So here I see 1 goes to 5. The next 3 all go to themselves. And 5 goes to 1. What's the cycle notation for this? Right, and so, again, this is where it's important, right? In cycle notation, we usually leave off things that are fixed. Right, because it's just a pain to write, in all honesty. So, I mean, you could write this as like 1, 5, and then the single cycles 2, 3, and 4, but why? And if you have the identity, right, then you would actually just write like E or whatever you want to call your identity, as opposed to like, I mean, you could easily call it this, or you could call it, you know, like 1, 2, 1, 2. I mean, you have a whole bunch of ways to write the identity, but we usually just go with the identity. We don't need to write it in terms of cycles. Okay. All right. What does the permutation diagram look like for the identity? Well, that one is pretty easy. So I was, like I said, looking through these beforehand, so I'll just go ahead and, yeah, it's just straight lines down, right? And in general, if we have in strands, it's just all of them going straight down vertically. Which is nice because then we can see its property as the identity, right? So again, this is a future problem, but I think contextually it makes sense right now. So if I wanted to see, I don't know, I don't want to do that one. Let's do gamma. So this is my E. So if you wanted to look at E and then gamma, so remember, we're doing functions here, right? We're thinking permutations are functions. So are we going left to right or right to left? Which one do we do first? Yeah, right to left. Good. And so when I write gamma E, that means E is going to be on top, right? And then my gamma would go, here I would make this explicitly 5, I guess. I'll just redo it. So 1 goes to 5. Jeez. Boom. Boom. I made a huge mistake in making this 5 and not like 3, but this is fine. Okay. And so we see this, and then what you do is you ignore this in the middle, and you just look at what happened from start to finish, right? So it's really like this guy went here, this guy went here, and these guys still just went to themselves. Well, this is just an elongated gamma, right? This is gamma. And you could obviously do the same thing where gamma is on top. And so, yeah, you can kind of see exactly what the identity is doing in terms of diagrams. And by the way, so diagrams are not just for like visualization and like getting used to permutations. Like people actually use these things. So like you can do a lot of interesting algebra by representing things with diagrams, and then do this like concatenation of diagrams, and like that's your operation. And you know, inversion is going to be, well, we'll talk about inversion in a second here, but yeah, you can do some surprising stuff with things like this, and some pretty cool stuff as well. We will do basically none of that, but just to know, it's a world that's out there that exists. Okay, so I guess moving on linearly here before we get to inverses. For S3, so first of all, how many things are in Sn in general? I know we've talked about this a long time ago. What's our order? Yep, just in factorial, right? You have in options for your first guy, right? If you think about it down here, and you have in, right? The first guy can go to any of these in once you choose it. Your second guy can go to any of the n minus 1 left, and so on, right? So for S3, right, we know we have 6 things. And we already know, like we've written generating sets, we've drawn the Cayley diagram for this. So for us in the past, right, when we talked about swaps as kind of our first little like geometric bit of intuition for defining a group. We talked about this, and so everyone is excited about N. I like it. Right, we had like E, we called it S12, like S23. These were kind of our generators, right? S12 and S23. And then we got our little hexagon from these guys. And then the last one, right, was you could do either order because they're equal. So it could also be S23, S12. Whoops. We're gone. We're back. All right. Yeah, so either of these could be equal. Right, so this is equal to S23, S12, S23. So we want to do a couple of things with this. So we'll talk about the cycle notation for all of these as well. But first, let's draw the diagram. So E, well, that's easy. All of these are on 3 strands, right? So E is this guy. S12, which, here, why don't you hit me with, as I do them, why don't you let me know what the cycle notation is for these? Okay, so I'm on S12. What is its cycle notation? And then I'll just draw. Wow, Mark, yeah, it is a Coxeter group. We definitely talk about this. So here I'm flipping 1 and 2. 3 is fixed. Yep, and so this is equal to 1, 2. S23, 1 is fixed. 2 and 3 swap. This is 2, 3. S12, S23. So here, this is important, right? So this is, I actually want to see, I want to talk about how to get products in terms of cycle notation here. So, I mean, maybe you already figured it out, but let's see what happens. So the way I think of this, right, is first I'm swapping 2 and 3. So you can do this, I guess, we can concatenate, right? So like 2 goes to 3, 3 goes to 2, this, and then 1 goes to 2, 2 goes to 1, and 3 is fixed. And so when you bring it together, you see that this is really 1 travels to 2, 2 travels to 3, and 3 goes to 1. Right, so this is my diagram. So what is this in cycle notation? Do we know? Yeah, so this is 1, 2, 3. But I think this is a decent point to talk a little bit about how multiplication really works here, right? So, because we already know these first two, right? So this is 1, 2 times 2, 3. But again, we're moving right to left. And so the way I view this is I just start tracking them, right? So I want to see, where does my 1 go? Well, my first one, it does nothing to 1, right? 2, 3 does nothing to 1. 1 goes to 1, and then I look at my second one, I move left, 1 goes to 2. Okay? So that tells me that I have like 1, 2. Now I need to figure out where 2 goes. Okay? The first guy sends 2 to 3. The second guy does nothing to 3, so 3 goes to itself. 3, and then 3 goes to 2 in the first one. And now I go to the second one, starting with 2, and 2 goes to 1. And so 3 goes to 1. Does that process make sense? So we're always moving right to left, and I'm kind of viewing it like cycle by cycle, moving right to left, and seeing where, tracking where it's going. Okay. So, I don't see questions. So S23, S12. So this guy, whoa. So here, right, 1 goes to 2. I guess, yeah, I can just do it the concatenation way for now. And then 2 goes to 3, 3 goes to 2, this is fixed, and so this is really 1 goes to 2 goes to 3, 2 goes to 1 goes to 1, and 3 goes to 2. Okay, and so what is this in cycle notation? One, 3, 2. Yeah. All right, and then our last one would be concatenating 3 of them. I don't really want to do it, so instead I want to show, okay, 1 goes to 2, which goes to 3, which goes to 3. 2 goes to 1, which goes to 1, which goes back to 2. And then 3, well, again, you know it's going to be bijective, so you already know it goes to 1, but we'll just do it. This goes to 2, which goes to 1. And so this guy is 1, 3. Okay? And so we have the cycle notation for all of these, and so another way to view S3 now, instead of using swaps, is we can see it as 1, 2, 2, 3, 1, 3, 1, 2, 3, and 1, 3, 2. So as the identity, it has 3 what are called 2 cycles, the ones with 2 on them, and then 2 3 cycles. Okay, and so we'll get a lot more into why cycle notation is very nice later. It's especially useful when you're talking about orders of elements, and it actually helps a lot in terms of what conjugates to what as well. Okay, so I'm not going to draw out the pictures. You guys have them in front of you. I already draw a couple. Is there a quicker way to produce these compositions? What do you mean by that exactly? Like to figure out what goes to what? In general, kind of. If you draw it a nice way. We will talk about that. So, yeah. Ricky asked if there's like a nicer way to do this, especially, you know, like we have this 1, 2 times 2, 3 is 1, 2, 3. Like this is not an accident, and we will talk a lot more about this when we talk about generating sets. I'm trying to look ahead as to where exactly we prove this. But basically, the things that meet in the middle like this, essentially you can always break things down into transpositions. These are called transpositions. These 2 cycles, basically because you are transposing their places, right? And so if you write them where they meet in the middle at 2, it will always adjoin like this. And so like if you have written it nicely, you can kind of immediately see what it's going to be. But if I just write you some random thing, at least right now, it's going to be hard to figure out what goes to what. But yes, we will learn much more about this. Okay. So what was our next problem here? So we wanted to talk about, right, so we've kind of talked about this already in terms of when do these things commute. So out of the alpha, beta, sigma, and gamma that we're drawn at like kind of the start of this section, which ones commute with each other, if any? Yeah, it's going to be beta and gamma. And the reason is what we talked about earlier, right? So beta is fixes 1 and 5. 2 goes to 4 here. 3 goes to 2. 4 goes to 3. And gamma was the one, oops, sorry. It's the exact opposite of this. 1 goes to 5, 5 goes to 1, and the 3 in the middle are fixed. right? And so basically this only affects these three, whereas this affects the first and the last. And so they just don't affect each other, and so beta times gamma is equal to gamma times beta, right? Oh, Clark, impressing, just because you have taken Greek class before, you've just got the sigma and gamma ready. Respect. Okay, so we've talked a bit about how the identity works, right? It's just strands coming vertically down, so it's very simple. When you concatenate with another permutation, you get it back. How do you find inverses? So we'll talk about a few ways to find inverses. So first of all, if I know right from our previous work early in the semester that the swaps are going to generate Sn. So if I just give you some word, right, and I give you, I'm just going to write sigma is sigma 1 down to sigma k, where each sigma I is a swap. Right? I don't know what I'm swapping, but I'm swapping a couple things. What is sigma inverse going to be? Any idea how to get the inverse from having written it as this product? Yeah, socks and shoes. So we're just going to do socks and shoes, and we get sigma k inverse down to sigma 1 inverse. And if they're all swaps, right, then these are actually just straight up equal to themselves, right? This is obviously very dependent on them being swaps. But in general, we can do this. If you just have cycles, right, that may not be two cycles, then you just have to stop here. Okay. How do we get it diagrammatically? So if I do, let's just do this part of beta here. So if I want to find the inverse of this guy, how do I find its inverse? Eddie, I think you had a really good description of how. I'm not sure if anyone else did. I didn't have a chance to read them all. Yeah, you reflect across this horizontal, right? Because to get the inverse, I mean, first of all, you have to go back, right? Because they would concatenate to the single strand. So like 1 went to 3, well, 3 must go back to 1. 2 went to 1, now it goes back to 2. And 3 went to 2, now it goes back. Now look at, if I reflect across this line, I have exactly reflected, right? So reflect. So you just kind of flip it over, you mirror that, and now you have your inverse diagram, which is pretty cool. Caleb, I didn't see yours. I'm glad to hear. I'm very proud of you. Okay. So then the last one is, if I show you a cycle, let's just say I have this cycle. This was my alpha from the book. How do I find its inverse? Any ideas? Because these are kind of our 3 different ways of thinking about permutations, so it's nice to be able to kind of be flexible and bounce between them. It's a thought. So let's look at this. All right. So let's look at the diagram and see what's going to happen. Wait. 5 goes to 4 goes to, yeah. That is the same thing. You were right. Yeah. I just had to think about it because you started at 1. Yeah. You just reverse them. And then, yeah, if you wanted to start with 1, then that would be exactly correct. So, yes. and again, it's this like cyclic permutation part, right? So 1 goes to 5, which goes to 4, which goes to 3, which goes to 2, which goes to 1. Like, these are the same things. And so, yeah, you just reverse it. And diagrammatically, right, like this one here is, 1, 3, 2. And then this guy here, you can see 2 goes to 3, 3 goes to 1, 1 goes to 2. And so you kind of see it there, and basically the whole point is wherever the thing went before, it's going back. And so like here, you're kind of ending at 5, and then, okay, 4 went to 5, so now 5 goes to 4. 3 went to 4, so now 4 goes to 3. So like that's the reason the reversing works, okay? All right. So yeah, now we're ready to state. We already knew this was a group, but now if you view it like as concatenation of diagrams or something, you can also see it's a group. But yeah, Sn is a group. We know how to find inverses. We know the identity exists. It's do nothing. Function composition is associative. And it is also a binary operation because the composition, this is maybe actually the hardest part, but composition of one-to-one and onto functions is still one-to-one and onto. And I mean, it makes sense, right? Like, the first map sends you to unique things, and then the second map also sends you to unique things, so the composition will send you to unique things. You didn't suddenly double up when neither of the maps individually did. Your first map hit everything, and then the second map, that means its domain is still everything, and then it also hits everything. And so the composition of onto is onto. Wow, 2 bots in very short period of time. Cool. Got to give that a little kappa, right? All right, excellent. So, figured this would be a good time. So we already did the cycle notation for S3, so we're basically done with what I've given you as an assignment. You can write down all 24 elements of S4 in cycle notation in your own time, because that sounds like the last thing I want to do, except for maybe like hang out with those bots. But I thought this would be a good time to talk through a few of these in 479, right? So try to get used to what's going on with multiplication, right? And kind of seeing some patterns that show up and just getting used to how multiplication is done using cycle notation, okay? So here we've got alpha is 1, 2, 3, 4, 5. Gamma was 1, 5. And so our first one is like alpha gamma. I'm actually going to write a couple. I want you guys to try to figure them out. So like, you know, a few people think about A. I'm not going to assign name. See if you can, yeah, figure out a couple of these. Alpha squared, alpha cubed, alpha to the 4th, alpha to the 5th. We want to try to figure out all these. So I'll give you a couple minutes, and I'm just going to, I don't know, twiddle my thumbs and do emotes in the chat or something. But I want you to think about these for a couple minutes and just see if you can figure out what's going on, especially as you increase powers. You should see a pattern if you do like B, C, and maybe just those two, but definitely by D. You should definitely see like what is going on as you multiply by that same cycle again and again. So yeah, we'll take a couple minutes, and then the last 3 minutes we'll just kind of finish at least these ones up. All right. Coxeter groups are cool. They say a streamer should never stay quiet for long. This feels weird to me. Sing? You don't want that. That's only for my neighbor who can probably hear me through the wall when I sing in the shower. Yes, that is correct. And we'll talk about why here in a second. Do I sing in Korean? I do a decent amount, yeah. But the problem is, having a bad voice translates in any language. So it's not like they're unaware. Yes, see, that looks right to me. I see a pattern. One of these should be super fast if you think about it, especially if you see the pattern. The dream is actually only to do alpha squared and then no C, D, and E from that. Okay, I'll let you guys keep working. I'm going to kind of start working through this. So if I look at alpha gamma, well, this is 1, 2, 3, 4, 5, 1, 5. So where does my 1 go? Right, so 1 goes to 5, which then goes to 1. All right, well, crap. So 1 doesn't do anything, right? So 1 goes to 5, which goes to 1. Okay, so I'll start it with 2. 2 doesn't do anything in the first one. 2 goes to 3. So 2 goes to 2 goes to 3. And then I'm not going to write all of that out. So the first one doesn't do anything to 3 or 4 either. 3 goes to 4. 4 goes to itself and then to 5. And then 5 goes to 1, which then goes to 2. So 5 goes to 2. And so that's how that one works, right? So 5 goes to 1, which goes to 2 is the last one. So alpha squared, this is where I want you to really think about what's going on. So 1 goes to 2, which then goes to 3. 3 goes to 4, which then goes to 5. 5 goes to 1, which then goes to 2. And then 2 goes to 3, which then goes to 4. And lastly, 4 goes to 5, which goes to 1. What's the pattern? Yeah, you said you see it. What is it? For alpha cubed, yeah. But here, so on this one, right, this is plus 2. So it's addition plus 2 mod 5. Right, so this is plus 2. 5 is 0 in mod 5. Plus 2 is 2. And then 2 plus 2 is 4. And then alpha cubed, now why is that true, right? Well, the first one sends it over 1, and then the next one sends it over another 1, right? Because that's all we're doing is we're just like pushing it to the right by 1, except for when you hit 5, going to the right means you go back to 1, and that's why it's like mod 5 addition, right? So alpha cubed, this should be immediate. So you should think plus 3 mod 5, and so 1 goes to 4, 4 goes to 7, which is 2, 2 goes to 5, and it's a little bit different than mod 5, right, because we're using 5 instead of 0. That's the difference, where 0 is 5, right? Like we're choosing to write that one. Kind of like on a clock, right? It's like mod 12, but we call it 12 o'clock instead of 0 o'clock, unless you're in military time. But yeah, the way we think of it, right, we have 12 on the hand, so it's kind of like that. And then it goes to 8, which is 3 mod 5. This should be addition by 4 mod 5. This is 1, goes to 5, which goes to 9, which is 4, which goes to 8, which is 3, which goes to 7, which is 2. And then what is alpha to the 5th? This was supposed to be the super quick one. Why? So you could do the addition mod 5. And plus 5 mod 5 is nothing. So yeah, this is E. And again, like you're cycling by 1. If you cycle by 1 5 times, you're back where you started, right? Cycle 5 times, back where you started. Cool. So yeah, hopefully you have a better idea of like how cycle notation works, how multiplication works, how to think through these things. Just always remember right to left, and you guys will get plenty of more practice on the next one. And this section in general is going to be pretty computational. We're really going to try to. There's a lot of like beautiful stuff with the symmetric group, and we're going to try to see how nice it is in terms of the generating sets, how to rewrite these things nicely in cycle notation. You can do a lot of cool stuff. All right, so have a delightful day. I'll be around for a few minutes before lunch if you have some questions. If not, I'll be around later if you have problem set questions or daily homework questions or project questions. So I will talk to you guys later.